to do that. And I just find it interesting, and if you haven't read the chapter, I'm going to make you, I just find this part interesting. There's a major point in this section. If sigma is not known but the relevant requirements are satisfied, we're going to use the student t distribution instead of the normal distribution, as is developed by William Gossett, which was lived between 1876 and 1937. Gossett was a Guinness Brewery employee who needed a distribution that could be used with small samples. The Irish brewery where he worked did not allow the publication of research results, so Gossett published under the pseudonym of student. So therefore, that's the reason why this one's called that student t distribution. It's just coming at it from a different perspective. Because if we're not having a large enough sample size, and if you're not knowing the population standard deviation, then we had to look at some other way of doing things. And he was taking that data and wanting to be able to use it, and so he had to come up with something that was going to work, which is where the student t distribution comes from. It is used if the distribution of the population is essentially normal, then we can use this t distribution where it's still taking the sample mean minus the population mean. So I'm still trying to figure out how far off it is. This is that margin of error that we're looking for, divided by the standard deviation of the sample over the square root of the sample size. So it's similar to what we were doing when we were talking about the z-scores, but I don't know the population standard deviation. And when we were looking at even finding the standard deviation of things, we were looking at there being a difference in how you find the standard deviation when you know the entire population versus the sample, and some of that piece is being applied as they were finding these t-scores. So the formula we're applying, if you look at what we're doing, zoom in a little bit closer, you can see what we're doing. The formula itself, really not any different. The only difference is, am I using a z-score or am I using a t-score? And so that t distribution is going to be a little bit different. The one of the big differences, a student t distribution for all samples of size n is often referred to as just your t distribution, and it's used to find those critical values. Your t distribution changes depending on the size of your sample. And so that's going to be one of the major pieces that we have to look at, is how big that sample size is going to help us find these t-scores as we do things. So it still had to be a normal distribution from the population is one of the key things we have to do. The number of degrees of freedom for a collection of sample data is the number of values that can vary after certain restrictions have been imposed. The degree of freedom is often abbreviated as DF. In this section, our degrees of freedom is the sample size minus 1. Degrees of freedom comes from the fact that if you go back and try to take your sample statistics, how many pieces of data do you have to have before you know all of them? So if I came in here and I said your guys' mean test score was an 82%. Well, knowing that, do you know what anybody in the classroom got? No. But if I came through and I told you, let's say there's, I've got 7 of you guys in here today. So if I came in here and I told you 6 of the scores, could you, and you know the mean score is 82, and I told you, well, the top 6 scores were, if you're really curious who the lowest, what that lowest value was, can you find it? Yeah, you can work your way backwards. If I only gave you 4 of the scores, could you figure out the last 2? If I tell you the mean is 82 and you know 4 of the 6 scores, can you figure out what the last 2 are? You can get close. You're going to still know, okay, their mean score was whatever, but you can't figure out, well, the last 2 people got an 85 and a 95. Might be that they had an 84 and a 96. You don't know what the last 2 values are. So the degrees of freedom is saying how many values do you have to know before you can find out everything. And so in this case, if I know the mean values, I have to know everything in the sample except for that last one, and that last one's the one I can figure out. So the degree of freedom is the sample size minus 1. Questions there? So knowing your degrees of freedom is your sample size minus 1 is going to be an important little detail to pay attention to. So now, if I was to rearrange my t-distribution, where again, this x bar minus the mean, the sample mean minus the population mean is my margin of error, how far off I'm going to be. Then, to figure out that margin of error, rearranging that previous equation, we're going to take the t-score, the student t-distribution of, again, alpha over 2, the standard deviation of the sample divided by the square root of n. Where the t of alpha over 2 has n minus 1 degrees of freedom. And we'll have to look at table A3 to be able to figure out what those scores are. So it does change depending upon the numbers of degrees of freedom. It changes what those t-scores are, even for the same confidence level, which determines what your alpha value is going to be. Unlike with the normal distribution, and we can have your mean of 0 and your standard deviation of 1, and we can just always move things around to where it fits into that box, and we can figure out our z-scores. We can't do that when our sample sizes are too small, or we don't know the population standard deviation. There's no way to force it into that box of what it needs to look like. And so the t-distribution just changes it each time for each one of those. This is table A3. And so if you look at it on the other thing so I can zoom in on stuff easier. Notice when we look at this, and again, this will be one of those tables that's given to you guys on your reference sheet that's part of your test. Just a little too close. So if we look at our t-distribution, a couple things to pay attention to. One of the things that it gives me, my degrees of freedom is along the horizontal, along the side. So the degrees of freedom is over here on the left. Across the top, it gives me two pieces of information. It gives me my area in one tail, and it gives me my area in two tails. So if I wanted to be 95% confident, that means in two tails we have a combination of how much? 5%. So my area in two tails would be the 0.05. Oops, that's the area one tail. Sorry, the area in two tails would be the 0.05. If it's 95% confident, what's the area in each of the little tails? 0.025. And so it's showing you the same thing. It's just lining them up. So depending upon what information you're given, if you know the area in one tail or the area in two tails. So right now, we're going to be figuring out the alpha is your area in your two tails. Alpha over 2 is your area in one tail. So it depends on which piece of those you're looking for, which one of those you'll use. But that determines which column I'm going to use. Now, unlike with your z-scores, we could figure out, we didn't have to know it to be 90%, 80% confident, 90% confident, 95%, 98%, 99%. Those are the only confidence levels we have here. With the z-scores, I could figure out if I wanted to be 96.5% confident, I could figure out what that was. If I wanted to be 83% confident, we could figure out what that is. There's not an 83% confidence that's on here. It's just giving you those most common confidence levels, and you just have to estimate with the closest values. Also notice on your degrees of freedom, we're very specific on the degrees of freedom until we get up to 40. Once you hit 40, it starts jumping from 40 to 45 to 50, 60, and you got to pick the one that's the closest. So round to whatever the closest value is when it comes to doing those. But your degrees of freedom is your sample size minus 1. When you have really small samples, then these values change quickly. If your sample size gets larger your sample size, the closer it gets to a normal distribution, and it's not as big of a deal with the changes. What was your question? Degrees of freedom is you're already going to know your sample size. Degrees of freedom is taking whatever that sample size is minus 1. So you don't have to worry about rounding there. But we will come back to doing the finding the sample size, and yes, we will round up. So that is a part of what we'll get to yet in a little bit. All right. So if I want to find the confidence interval for the estimate of the mean when the standard deviation is not known, First of all, the requirements have to be met that it is a simple random sample. Should sound really familiar that if you are reading something and it doesn't tell you it's got a good sampling technique, that you know that's already wasted, useless information that we're not even going to use. And again, either or both of these conditions have to be satisfied. Either the population is normally distributed or the sample size is greater than 30. Same restrictions we've had before. And so as long as one of those two things is met, we'll be able to use this. Notation, mu is still the population mean, x bar is still the sample mean, s is still the sample standard deviation, n is still the number of sample values, e is still my margin of error, and then the t of alpha over 2 is the critical t value separating an area of alpha over 2 in the right tail of the t distribution. Finding my confidence interval. Again, not much difference than what we've done before, where you're taking your sample mean minus the margin of error, your sample mean plus the margin of error to be able to give me my confidence interval that my population mean has to be somewhere in between, population mean being mu. To find my margin of error on these, though, when I don't know, and this is key, is sigma is not known on these. To find my margin of error, you're going to use your student t-score, so the t of alpha over 2 times the sample standard deviation over the square root of n, where the degrees of freedom is the sample size minus 1. So let's do one. Let's look at number 22. Acupuncture for migraines. In a study designed to test the effectiveness of acupuncture for treating migraines, 142 subjects were treated with acupuncture and 80 subjects were given a sham treatment. The number of migraine attacks for the acupuncture treatment group had a mean of 1.8 and a standard deviation of 1.4. The number of migraine attacks for the sham treatment group had a mean of 1.6 and a standard deviation of 1.2. Part A, construct the 95% confidence interval estimate of the mean number of migraine attacks for those treated with acupuncture. First good question I guess I should ask, do I know the population standard deviation? That's just from the sample. Do I know the population standard deviation? I don't. And that's more realistic. If I'm trying to test for acupuncture, I probably don't already have sitting in my back pocket what the standard deviation for the entire population is, because if I already knew that, then I probably have done enough research that I probably should have a pretty good estimate for the mean. And so it's not very likely that it's already been done and I'm just repeating somebody else's work and I can use what they've done. And so that means since I don't know the population standard deviation, I have to use my student t distribution. And so I'm using that E is the t of alpha over 2 times the standard deviation over the square root of n. So now that I'm using that part of things, what will I use for S? Well, actually, let's do the the t first. What is t of alpha over 2? First of all, what is alpha? Okay. Alpha, I'm wanting to be 95% confident, so alpha is going to be the 5%. Is that going to, just do it this way. Alpha is the 0.05. And so that's the area in, which one? One or two tails? It's the area in two tails. What is my degrees of freedom? Okay, degrees of freedom, because this is going to be the 141. Because this is looking at the ones that were treated, and there's 142 of them that were treated. So if I have to use my degrees of freedom as 141, So when I come over here to my degrees of freedom, what number is closest to 141? 100 is as good as I get. Am I doing, which column am I looking for? Okay, the one that has two tails is the 5%, so I'm looking at that middle tail, or middle column. So the T is, I'm sorry, you guys can't see 1.984. So now to find my margin of error, we're using the 1.984. What is S? Okay. S was my sample standard deviation, which is what for the acupuncture people? 1.4 over the square root of n, and what was n? Give you guys a moment to use your calculators to do the arithmetic. Now, I'm wanting to know my confidence interval. This is telling me my margin of error. First question I think I do want to ask on this one, what will be my rounding rule at the end? Just from what we've already been doing with rounding rules, what should we do? Which one is it? Same number of decimals or one more? Same number as which one? Same number of decimal places as the original statistics that we had. And the piece I haven't written down on here yet is, what was the sample mean? So since my sample statistics have already rounded that to 1.8, my sample standard deviation was already rounded to 1.4. Both of those were already one more decimal place than the original data was. So when we get to our answer, we're going to only round it to one decimal. Now, I want my final answer to be what's rounded. Don't round the margin of error in the middle of it until I get to the very end. So to find my confidence interval, we're going to take the mean and add and subtract that margin of error. So you're going to take your mean, which is the 1.8, subtract off the margin of error, and the mean, and add that margin of error. So we want to not have any rounding errors too much too soon, because you don't want to round and then round and then round, because then you get rounding errors in the middle of that. So keep those extras till we get to the end, but we're going to round our final answer to just one decimal. I'm trying to remember what we were deciding on. This is the mean number of migraine attacks for those treated with acupuncture. So those people treated with acupuncture are going to have, the true mean of the population is they're going to have between 1.6 and 2.0 migraine attacks. It doesn't tell me what my time range is for whatever that time period is that they're looking at. Questions on that? Now, what if I could use the calculator to do it? If I could leave this part out if you'd like. There is an easy way, but understanding where it's coming from is important. To use this one then, we're going to use the t-interval. So that's the reason why I was really pointing out whenever we were doing stuff that we were using the z-interval because we were using the z-test. Now we're doing the t-test, the student t-test. You're going to use the z-interval when you're going to do it. So paying attention to, do I know the population standard deviation, then I use a z-score. If I don't know the population standard deviation, I use the t-score. Actually, before I do that, let's use the calculator and do the next one. Let's do part B on number 22. So number B is construct the 95% confidence interval estimate of the mean number of migraine attacks for those given a sham treatment. So if we are using this one, we'll go into our stats, arrow over to tests. We'll have to go down to number 8, which is the t-interval. And again, keeping in mind that you would use your student t-score if you don't know the population standard deviation. This time we know the statistics. What was the sample mean for the sham group? That was the 1.6. What was the standard deviation for the sham group? Now, this is one place that hopefully, if you haven't figured out which one to use, that just the notation here should trigger some reminders. S sub x, S is your sample standard deviation. So this is really screaming at you. This is when you're using the sample that you would put this information in. We'll come back to the other one. What is N in this case? No. It was the 80 this time. So there's only 80 of them in the sham group. What's my confidence level? I want to be that 95% confident. Now this one takes a little longer to do because the calculator has to do more work because it doesn't have the just nice friendly z-score that's the same for all sample sizes. It had to calculate out for that sample size. But it gives it to me. Now how many decimals do I round my answer to? Okay, I'm going to round it to 1 decimal, so I'm going to have it between the 1.3 and the 1.9. And I'm going to 1 decimal because the sample mean was to 1 decimal and it's already been rounded to that place value. So you round to the same place we already have. Now, part A, we had our confidence interval of 1.6 to 2.0. And this was for when we had the acupuncture. For my sham group, we just found it to be 1.3 to 2.0. So my mean is somewhere between 1.3 and 2. Is it 2.0? 1.9. So now, compare the two confidence intervals and what do the results suggest about the effectiveness of acupuncture? If this is talking about the mean number of migraines. Okay, didn't really change it that much. Because what this is telling me is the true mean of the population somewhere in there. Almost looks like the sham group could possibly be better than the acupuncture group because the population mean is somewhere in here and it could be as low as the 1.3. It might be as high as the 1.9. And the acupuncture group somewhere in here. So it could be as low as the 1.6, but it could be up as high as the 2.0. So there's a chance that the sham group might have more migraines than the acupuncture, but there's a chance the acupuncture might have more than the sham. It's just they're in there somewhere. There's one right answer. I just don't know what that right answer is. It's captured in that range somewhere. So does this say that you should spend some money doing some acupuncture? Based off these results, it's not suggesting that that's a really wise choice. Now, this is just one sample that we're really considering as we do this. But it does not look like the acupuncture group does a lot better than the sham group. Questions there? Okay, now some important properties we do need to know about the student T distribution. Some of these I've kind of mentioned as we've been going. One of them is that the student T distribution is different for different size samples. So if we looked at the blue is the normal distribution. If I have a small sample size, I'm going to have more variety. I'm going to have a lot more variation between things than if I had a really large sample size. And so the student T distribution changes based on that sample size. When my sample size was only 3, that's this yellow line, then notice how it goes out further into having more in those extremes. That if you only had 3 in your sample size, you have the possibility of getting more of those extreme values. You don't have as many in your sample to balance each other out. If you only had, if we're talking about heights, and you're only taking 3 people in your sample, and you happen to pick somebody that is 7 foot tall in your sample, then that one person has greatly changed what the mean value is in your sample, the mean height. On the other hand, if you are doing samples that have let's see, this had 12 in it. If you had 12 people in your sample and you have somebody that's 7 foot, it's still making your height, your mean height, larger than what it would normally be, but not as drastically. That one person doesn't make as big of a difference. If we had 50 people in our sample, having one person who's 7 foot tall will make a little impact, but not a huge impact. It's not going to pull it a long ways away from the true population mean. And so that's what this is doing, is it's saying if you only had 3, you might get the two extremes. You might get something that's extremely small. You might get something that's extremely large. It's more likely to occur. And remember, the area under that curve is talking about the probability, the likelihood that it happens. When it gets to be 12 in our sample, it's getting it closer to that normal distribution. You still have more extreme than you would if it was a normal distribution, but it's getting a lot closer. Compared to the larger your sample size is, the closer it gets to that true normal distribution, which is part of the reason why on our tables that we don't have it as accurate as we get those larger sample sizes. So knowing that it's different for each sample size, the student T distribution has the same general geometric bell shape as a standard normal distribution, but it reflects the greater variability, so wider distributions, that is expected with your small samples. So it still has that normal shape, that bell-shaped curve. The student T distribution has a mean of T equaling 0, just as the standard normal distribution has a mean of Z equaling 0. So your mean is still 0 in the middle, so you still have a possibility for positive and negative T scores, just like we could have positive and negative Z scores. The standard deviation of the student T distribution varies with the sample size and is greater than 1, unlike the standard normal distribution, which had a population standard deviation of 1. So your standard deviation is not staying consistent from one value to another. The standard deviation of the actual distribution changes depending on the sample size. As the sample size n gets larger, the student T distribution gets closer to the normal distribution. So these are kind of all things that I've mentioned off and on throughout things, but I wanted to put them all together to make it a little easier to know what we're really dealing with when we talk about the student T distribution. Now, how do I know what to do when? First of all, if you're talking about trying to figure out the confidence interval for the mean, the first question to know is, do I know the population standard deviation? If I know the population standard deviation, the next question, is the population normally distributed? If it's already a normal distribution, then we immediately go down to using the Z-score. So you're going to use that Z-score, which is your normal distribution. And so if you're doing it on the calculator, use the Z interval. If, on the other hand, we knew the population standard deviation, but it's not a normal distribution, so the population itself is already skewed, then the next question is my sample size larger than 30? If my sample size is larger than 30, then I still get to use my normal distribution, so I'm still using the z-interval on the calculator. If my sample size is not larger than 30, then I have to use some other method. The other method we would use is the non-parametric or the bootstrapping method. We're not learning about that this semester. So if you get to where you don't know the population standard deviation and your sample size is too small, then we just can't do it at all. So for this point in time, we would just say, I can't calculate that out. So if I was looking at, a lot of times with test scores, I get bimodal, where I get people that do great, I get several people that do not great, but I don't get very many people in the middle. Well, if you're looking at that kind of distribution, if I only took a sample size of 3 students, then it's not going to get to be able to use that t-scores, because that's not a nice normal distribution. And so if you only had 3 in your group, there's no way to turn this sample sizes of 3 into a nice normal distribution. If it was bimodal and I had 100 in my sample, taking the distribution of that would actually go back to being a normal distribution. Even though we took stuff that was not a normal distribution to start with, large enough sample sizes actually kind of smooths that back out. Now, so when we know the standard deviation of the population, we'll either use the z-score or we don't have enough information. If I don't know the population distribution, the population standard deviation, then the next question still is, if I don't know it, is my population normally distributed? If it is, I get to use my t-distribution. So on the calculator, you will use your t-interval. If it's not normally distributed, my question still is it 30 or larger? If it's larger than 30 in my sample size, I still get to use my t-scores. If my sample size is not larger than 30, we're back to using that bootstrapping method that we're not going to use this semester. And so we still wouldn't be able to calculate it out. But those are things to think about, because once in a while you'll run into those trick kind of questions and you try to force it into something that you don't already have. Now, if you know the confidence limits, so calculator's spitting out the answer of it's in between the 2.9 and the 4.1. Well, how do you figure out what the actual mean and the margin of error are? These are the same things that we've done before. If you know the limits, to find the find the sample mean is that middle number. So you add the extremes, divide by 2, because it's your middle value. If I'm wanting my margin of error, how far off would I need to add and subtract to get those limits? To find that, you figure out what the difference is between your limits. You take your biggest value minus your smallest value, cut that in half, and that tells me what I would add and subtract from those. So again, this is something we've done before when we were working with it with the z-intervals. Finding the point estimate and the margin of error from the confidence interval then. So given the confidence interval, 73.6 to 78.4, find the sample mean, which is your best point estimate of the population mean, and finding your margin of error. We can't figure out the sample size if we don't know the population. Okay. Just trying to figure out I thought we were missing sample size, but we're not. So what is your sample mean? So 76. What is my margin of error? We're going to find that difference between the two things and cut that in half. You said 2.4. So another way that I could write this, so if I was wanting to write this in some sort of research report, I knew my confidence interval, but I knew people won't really understand that nearly as well as they would say, well, the population mean is the 76 plus or minus the 2.4. So it still is telling me the same thing. It's saying my sample mean was 76. I know my margin of errors. I could be off by as much as 2.4, whatever those units are in either direction. So So it's still expressing the same information, just two different ways. All right. Homework then from section 3 or 7.4. The test is scheduled for Friday, so it's on Wednesday we will talk about finding the confidence interval for the variance and the standard deviation. Friday then is when you guys are ready for the test. Friday I'm not going to be on campus. I've got a meeting in Rolla on Friday. So your guys' test will be in the ARC on Friday. Yep. So we will not have class on Friday. You'll just need to take your test Friday. I guess if you really wanted to, I can make it available Thursday night. Okay. Then the extended problem then won't be due until next Monday for this. I'll give you guys the extended problem next time. So I wanted to cover all the different things before I had you thinking about it. And don't forget, you can start registering for classes on April 2nd. So start meeting with your advisors so that they have you authorized to be able to register as soon as you want to. And that's for either summer classes or next fall.